We're living through a pandemic, and countries have been working frantically to flatten the curve. But how? And how do we know in the midst of this pandemic? Well, to answer these questions, we need the SIR disease spread mathematical model. During a disease spread, this model splits a population into what we call susceptibles, infectives, and removed, which all feed into each other, as represented by the arrows. Now you might ask, well, what do these groups represent? Well, susceptibles represents people who can catch the virus. With COVID-19, a novel virus, everyone is susceptible, no one's immune. Infectives are just people that have the virus and can spread it. Removed are people that have died or recovered. How do these groups feed into each other, as I previously mentioned? Well, in a pandemic, susceptibles and infectives interact, and so the susceptibles catch the virus and they become infected. Infectives eventually recover or die, so they move to the removed group. All this happens at rates of change. Susceptibles, infectives, and removed change over time. Susceptibles change by a decrease, hence the negative sign, because they lose individuals that are susceptibles who are turning infected at a rate A of transmission of the disease when they interact with infectives, as represented by the SI term there. This loss of susceptibles is a gain in infectives, which also lose individuals at a rate B of removal or recovery, moving into the removed group. Now, let's see the SIR model in action. Imagine a town called Square that's just been attacked by a virus. Will this virus spread and turn into an epidemic or even a pandemic? Well, for that, we need to do some mathematical manipulation. Well, when disease is spreading, that basically means that there's a rising number of infections, and mathematically speaking, that's a positive rate in the increase of number of infections, hence the greater than zero symbol. And solving this inequality would yield the following quantity. This quantity we've just found is known as the reproductive number, and when it's greater than 1, we would have a rising number of infections. Could be an epidemic or pandemic. This quantity also tells us how many people an infected person can infect. For example, with COVID-19, it's a pandemic because the reproductive number is approximately 3. So one infected person can infect 3 other people on average. And that's quite troubling. Now let's have a look at this infections against time curve. This is the pandemic curve, rapidly increasing at first, exponentially increasing, then eventually dying out as people start to recover and precautionary restrictions are maintained. Since this curve resembles a pandemic, that means the reproductive number is for sure greater than 1. The other possibility is that the disease isn't infectious enough, so a pandemic wouldn't start and the reproductive number would be less than 1. And we know that this A over here is the transmission rate, and it's very important to focus on this transmission rate because it's the key to flatten the curve. The higher it is, not only will it make the reproductive number greater than 1, but will also make the virus more infectious. Notice that at a high transmission rate of 5, we get this typical pandemic growth curve, rapid increase in the number of cases. And if we take control and lower this transmission rate, we flatten the curve. Alright, so although we can't control how deadly the virus is, or how fast someone recovers from it, we can certainly control things such as this transmission rate. And we can do this by means of taking the necessary protective measures, which would give the virus less chances to transmit, such as staying at home, wearing a mask, and certainly washing our hands. We're in this together, and thank you for watching.